Hi everyone, this is a video to go over some properties of logarithms and the power rule in general. So the first thing we want to do is go over the proof of one of the properties, which is that if we multiply two things inside an ln function, then that will turn into the addition of the ln functions. So when we start a proof, we want to start with the word proof. We want to make sure that our proof falls within the column that's created by the word proof. And since this proof has some pretty intense u substitution, I'm making this blank spot to just do some scratch work on the side. So let's start with our let statement. We're going to let x and y belong to the real numbers, and we need those to both be greater than 0. And x greater than 0 and y greater than 0. We're going to use the addition property of integrals, so we also need a statement about whether or not x or y is bigger than the other. So 0 is less than x, as we just stated. And then we would need a less than or equal to, thanks for that less than or equal to, Joe, x and times y. This would only be true if y is greater than or equal to 1. We can go do some scratch work for that real quick. Let me change colors. If we have x is less than or equal to xy, then we just divide both sides by x, assuming that x is not 0, which we already assumed right here. Then we just have 1 is less than or equal to y. We need this because when we use the additive property, we need x to be between our limits of integration. Since we have the formal definition of a limit, we know of a natural log, we're going to integrate from 1 to y. So having this restriction that y is greater than or equal to 1 is not going to be a problem. Okay, going back to our formal definition, we have that the ln of xy is equal to the integral from 1 to xy of 1 over t dt. Note on the side here that this is sometimes written as 1 xy dt over t. It means the same thing, it's just shorter notation. Alright, now we want to use that additive property. I want to split this integral into two pieces. If I do that, I'm going to split on x because that will give me an ln of x right away. So this is equal to 1 to x, 1 over t dt, which is the definition of ln for x, plus x to xy of 1 over t dt. And this is why I need x to be in between x and y. I can't say all these x's and t's at the same time and still write them down correctly. So this is why I needed x to be between x and y, so that I could split it on x, which isn't true if x is somehow outside of 1 to xy. So by definition, this is ln of x. And by some crazy u substitution, this one is ln of y. So we're going to write that down, and then we're going to go over here and do that u substitution. So what we're going to do is let u equal t over x. And we're just going to try and deal with how many variables that will leave us with. So u is equal to t over x. Well, that means if we were going from x to y, so if t is equal to x, then u would be x over x, which is equal to 1. If t is equal to xy, then u is equal to xy over x, which is just equal to y. So our limits of integration will be correct. Now there's no u over here to plug this into, and t is not by itself, so we've got to fix that. So if u is equal to t over x, then t would just be equal to ux. Let's multiply both sides by x. So if I plug that into the integration, it would be from 1 to y of, and let's see, that would be 1 over ux. But I don't have my du yet. So let's go back up here. I'm going to have to do a du. So du is equal to, I need a dt, 1 over x dt, which means that x du is equal to dt by multiplying both sides by x. So that means that this on the numerator has to be an x, and this can be now a du. The x's would cancel, and that gives me a 1 to y, 1 over u du. That's a y. Okay, so this ends up replacing this entire integral by doing this u substitution. U is equal to t over x. And a lot of the textbooks will just literally write that down and move on. So what you're missing is how the u substitution works and why it changes the limits of integration. So now we have, therefore, ln of xy is equal to ln of x plus ln of y. Tombstone, or QED. Okay, now we're going to prove another property, and this time it's going to be for exponential functions. So we're going to start with our proof. There'll be a lot less scratch work on this one, so we don't need to make the margin. And we're going to start with our lets. For this, we just need let x1 and x2 belong to the real numbers. Okay, we're also going to let y1 equal e to the x1 and y2 equal e to the x2. And then we're just going to start our proof. So this gives us e to the x1 plus x2 is equal to e to the ln of y1 plus the ln of y2. And this works because, I'll grab another color. We have, for example, y1 is equal to e to the x1. So if I just take the ln of both sides, those two things would cancel, and I would just get ln of y1 is equal to x1. Okay. So by the properties of logs, e ln of y1 plus, times y2, and these two things would cancel, which would leave me with y1 times y2, and going back to what we defined those to be, we have e to the x1, e to the x2. Therefore, e to the x1 plus x2 is equal to e to the x1, e to the x2, tombstone. This one is definitely not as bad, it's the log one, but that's because we had the log properties already when we started our e function. So by our textbook, we define all of the ln, which makes sense mathematically, and then from there, we define this alternative function or the inverse function e, and since we had the ln already, we could use it in our proofs here. All right, so now we're going to move on to the general power rule, which we're now going to extend from the rational numbers, which is all we've defined them for in the past, and we're actually going to include the irrational. And we're going to do that by using the e and ln functions to be able to find the derivative and show that it works for both rational and irrational, or in other words, all real numbers. Okay, so to do the extension, we need to rewrite this using e to the x. So let's look at d dx of x to the p, which is the same as d dx of, here's the weird part, e to the ln of x to the p, oops, big parentheses. Those two functions would just undo each other, they're inverses. So with that's the same as d dx of e and then using the properties of ln, p ln x. Ooh. All right, and now we're going to use some chain rule to take this derivative. So that is chain rule, derivative of the inside function would just be the constant in front, and it's a dx, so p doesn't count, it's just a constant. The derivative of ln of x is 1 over x. And then times the outside function, e p ln of x. But we've already said that this whole thing right here is just this, right? We just wrote it using these two notations to look like this. So I can easily change it back. P, 1 over x, I'll use parentheses to emphasize what's being multiplied here, x to the p. So that is p, x to the p over x, which can be written as p, x to the p minus 1, because when I move this to the numerator, it's just subtracting 1. Just like x squared over x would be x squared minus 1, which is just x. But here, p is any constant, so we're just using it as a placeholder. Okay, so that's how we can extend to all rational numbers. Why on earth did we do that? Because it makes it a lot easier to deal with far more complicated problems, like x to the 2x. How do I take the derivative of that? So d dx of x to the 2x, I've got a derivative in, or I've got a variable in the base and in the exponent. What we're going to do is use this trick to take that derivative. All right, so chain rule, well, actually, let's rewrite it first. That's d dx of e to the ln of 2x. All right. Sorry. That erase. X to the 2x, so e to the ln of x to the 2x. That x is super important. And that's the same thing as d dx of e, moving this out in front, 2x ln of x. Ooh. All right, we're going to need chain rule again. So the derivative of the outside is the easiest one because ln, or because it's e. This is e, 2x ln of x, and we'll just write d dx of the inner function, which is 2x ln of x. We'll deal with this in a second. This is product rule. Not how you spell rule. Rule. There we go. Okay, we've already said that this guy is just right there, so might as well write that down. That's x, 2x. And now let's deal with this product rule. So product rule is f prime g plus g prime f. So 2, and then the second function, so this is f, and this is g. So f prime is 2 times g ln of x plus g prime is 1 over x times f is 2x. And now just simplifying, we have x 2x ln of x squared, and then boink, boink, plus 2. The book simplifies this differently. It does, let's do an arrow. It factors out the 2. So x squared x 2 ln x squared. Just kidding, we move that x out in front, or that 2 out in front, plus 2, and then they factor out the 2. 2x of ln x plus 1. So these two answers are essentially the same, just one has a 2 factored out.